Ustedes me dicen, ¿ya? Ah, muy bien. Bueno. Pues buenas tardes a todas y todos. Bienvenidos al Auditorio Sánchez Vibriesca de la Torre de Ingeniería. En esta ocasión es un placer para nosotros, el Instituto de Ingeniería, y de manera particular muchos amigos del doctor Hong que estamos aquí, de invitarlo para que nos haga una presentación de algunas cuestiones de sus últimos artículos, ¿no? Múltiples artículos. Bueno, y desde luego también bienvenidas y bienvenidos a todas y todos que nos están viendo desde la transmisión en línea, tanto a los colegas del Instituto de Ingeniería, también a las sociedades técnicas, de manera particular a la Sociedad Mexicana de Ingeniería Sísmica. Pues sean todos y todas bienvenidos. Voy a leer una semblanza del doctor Hong para que los que no tienen el gusto de identificarlo, pues tengan una idea de su trayectoria. El doctor Hong es profesor de la Universidad del Oeste de Ontario, en Canadá. Él obtuvo el título de ingeniero civil en la Facultad de Ingeniería del UNAM en 1984, obteniendo el premio al mejor estudiante de ingeniería civil y la medalla Gavino Barreda. Bueno, él me dijo que no leyera esto porque no le gusta, pero creo que es importante para que lo conozcan. También obtuvo los grados de maestro en ingeniería y doctor en ingeniería aquí mismo en la universidad, bajo la supervisión del doctor Emilio Rosenblut, que pues también es un investigador emérito, fue un investigador emérito pues conocido de manera nacional e internacional y que trabajaba aquí en la universidad. En sus estudios de maestría, el doctor Hong fue también merecedor a la medalla Gavino Barreda por su excelente trabajo, y también le dieron el premio Weizmann a la mejor tesis doctoral. Entre los trabajos que desarrolla el doctor Hong, pues él aplica la teoría de probabilidad para el estudio de espectros sísmicos, modelos para la generación de sismos de subducción para México. También, como parte de sus actividades, él también trabaja mucho en el análisis probabilista de sistemas de ingeniería civil, cálculo del peligro sísmico, riesgo ante eventos sísmicos, y bueno, no nada más sísmicos, también eólicos y también cuestiones relacionadas con nieve, ¿no? Calibración de códigos basada en confiabilidad y la aplicación de toma de decisiones bajo incertidumbre. Ha publicado ampliamente en los temas mencionados. Pues a lo largo de su trayectoria ha publicado más de 200 artículos en revistas JCR indizadas, pues más de 80 artículos en memorias de congresos y alrededor de 50 reportes técnicos y un libro. El libro, por cierto, con el doctor Katsugoda. También ha dirigido un total de 26 tesis doctorales, quizás ya está un poco desactualizado esto, y 31 de maestría, ¿no? Yo creo que ya son más. También el doctor Hong ha sido merecedor a múltiples premios y reconocimientos por sus aportaciones en las áreas de investigación. Es miembro activo de varios comités canadienses de diseño de código, incluyendo el Comité Actual de Diseño Estructural del Código Nacional de Diseño de Edificios canadiense. Es también miembro del Grupo de Trabajo de Calibración del Código Canadiense de Puentes y del Grupo de Trabajo de la Asociación Canadiense de Normas para la Revisión de los Lineamientos para el Desarrollo de Estados Límite de Diseño. También es parte del grupo de editores de varias revistas internacionales reconocidas y de gran prestigio, y de comités técnicos para diversos congresos internacionales, algo que muestra la gran relación que tiene el doctor Hong con México. Es, además de sus contribuciones, también en 2012 el doctor Hong ingresó a la Academia de Ingeniería de México, a la Comisión de Especialidad de Ingeniería Civil como académico correspondiente, por sus aportaciones en las áreas de peligro, riesgo y diseño sísmico óptimo, con especial aplicación, pues como lo mencioné, a México. Y en 2016 fue el ponente de la conferencia magistral Emilio Rosenblut de la Sociedad Mexicana de Ingeniería Sísmica. Bueno, pues este es un panorama para que conozcan al ponente que tenemos en esta ocasión, y pues sin más, invitamos al doctor Hong a su presentación. Muchas gracias.
Gracias, doctor Pozos, por la introducción. Gracias por venir, amigos y amigas, a esta presentación. Mi disculpa, no puedo dar esa conferencia en español, pero si después, si ustedes tienen preguntas, por favor, hace en español, inglés o chino, está bien. ¿Okay? Hoy lo voy a discutir o compartir con ustedes unas cosas que desarrollamos sobre analizar, modelizar y simular procesos no estacionarios gaussianos. Okay. Voy a empezar a hablar en inglés. So the title of my presentation is Use of Transform Pair to Analyze, Model, Simulate Non-Stationary, Non-Gaussian Processes with something we call IPAC algorithm. I will explain what that means, and I will emphasize its use to model or simulate seismic ground motions. So my name is Hanping, and I'm from Department of Civil and Environmental Engineering. Western Ontario is in London, Ontario, about 2 hours from Toronto, and here is my website. So if you want to send me some questions later on, please do so. Okay, my presentation is focused on 3 parts, and because I do not know the audience, so first I'm going to discuss a review of basic concepts. Then I'm going to talk about the non-stationary process. In particular, I'm going to talk about the evolutionary process. What is its definition, how it is used in the literature, and what is the most effective way to simulate evolutionary process. All these are available in the literature. Okay? The third part is what we are going to talk, or we did, and it's called iterative power and amplitude corresponding correction algorithm. We're going to talk about, in particular, I'm going to emphasize S-transform, continuous wavelet transform. We are going to use the IPAC algorithm for non-stationary, non-Gaussian or Gaussian cases. We simulate single process, random field, and the vector of processes. Finally, I'm going to discuss about its use for conditional simulation of non-stationary, non-Gaussian processes. Okay, so let's start with the basic about using Fourier transform in dealing with signals. Essentially, if we use Fourier transform, what we have is, think about this is a ground motion. If you apply Fourier transform, what you obtain is amplitude of Fourier coefficients plus phase. Phase is very, very strange. There is no clear pattern. However, the amplitude is something like that. So at low frequency, you have something and keep going for this particular signal. One of the things that is interesting for Fourier transform is that if you apply Fourier transform, you get the signal, you go back, you get this, and the Fourier transform is non-redundant transform. In other words, if you have 10 numbers in here, you get 10 numbers on the other side. 5 corresponding amplitude. If you assign a signal based on Fourier domain, you will get the signal. When you come back, you get the same thing. So that's extremely important for our discussion. So if you want to represent the coefficient of Fourier in time and the frequency, it says at any time the Fourier amplitude is the same and the Fourier phase is like this. It's constantly in time. Therefore, Fourier transform is very good in dealing with stationary process. And of course, we have something called the Parseval theory. the energy in time domain and in Fourier domain is the same. So energy preservation. Without energy preservation, we are in trouble as well. So you have something like amplitude of Fourier coefficient, and you go to time domain, you will not get the same as energy. So that's no good. But in this case, yes, there is famous theory, Parseval theory, and establish this. Okay. Sometimes, like when we use Fourier transform to simulate signal, looks like very mysterious. Actually, it's not. You think about the Fourier transform pair and describe it in discrete form. You can write it in this way. So in other words, you can see the signal can be constructed using an amplitude times exponent. This is frequency and times phase. So given a signal, you obtain this, and given the phase and amplitude, you're getting back to this. This is in discrete form. Again, I should emphasize non-redundant transform, Fourier transform, and this perfect reconstruction. In other words, you apply Fourier transform to signal, you apply inverse to the Fourier coefficient, you get the original signal. You apply inverse Fourier transform assigned coefficient, you get the signal. Then you apply Fourier transform to the signal, you get the same Fourier coefficient. Change of the phase results in different signal, but the Fourier amplitude remains the same. In other words, the energy in frequency domain is the same even you change the phase. You will have two signals looks kind of very different, but it is energy content in frequency is the same. Okay, so why is it important? It is important to describe a stochastic process. According long time ago, Kramer provided this spectral representation. It says a stochastic process is defined by exponent e 2 pi ft. This is Fourier transform. But this is strange for civil engineers, usually, DZF. In other words, there is something here that is function of frequency, but we cannot write it out. Cannot be derived in everywhere, but you can integrate. Of course, there's other things that based on statistics says should have orthogonal increment. In other words, two frequency different, the energy is zero, otherwise you have density function, power spectral density function times dt. Now, as a good engineer, I will say, you tell me this cannot written in derivative. How about I said delta z? If I replace this by delta z equal to amplitude of some kind of stochastic process times EI a phase, I substitute that, what I have is this representation. And in other words, as long as I know the phase, I can generate in non-stationary process using this representation. That's why, based on Kramer's representation, what we can do is we can generate in samples of this stochastic process. It's so simple. So you think this way, there's not a lot of math except you discretize this, and this is what you written. Here will be power spectral density, here is increment of frequency, and here is the phase angle. So in other words, given a sample of a stationary process of length t, we can calculate a parallelogram of the sample defined as Fourier transform multiply its complex conjugate divided by duration. That's why it's density. And you have one side, there's two sides, the power spectral density. That's a minor issue, but essentially we are saying, given a signal, we can calculate the parallelogram, and for simplicity, I will say simply says power spectral density, and the amplitude of Fourier transform is given by this quantity. Okay, now we have concept from Fourier transform to stationary process, and this took us 10 minutes to understand stochastic process. In a sense, you keep looking this, you will find out that the so-called spectral representation method, SRM, developed by Shinosuke and Jane in 1972, later on with his co-workers, Deodatis and others. And you have this kind of representation. In other words, if you want to generate a signal, you can get this. Okay, so you have here inverse Fourier transform given power spectral density and the phase angle, you write in this way, independent uniform distributed phase angle between these. So alternatively, I can represent it this way. It's simple. So the trouble, couple of things, is that this is Gaussian. Why is Gaussian? You see, this is summation of many terms. According to central limit theory, no matter what you do, after many, many terms, this must be Gaussian, okay? This can be carried out fast Fourier transform to gain efficiency. There is another form of SRM. So in other words, it's uncertain coefficient for cosine and sine. It's same as Fourier transform. I will not elaborate further on that. You have something called uncertain amplitude and phase representation as well. It's a minor issue in our presentation. It's important. So the spectral representation method for stationary non-Gaussian process according to the translation theory, you can write that way. In other words, you simulate a Gaussian process, you calculate its probability, you apply an inverse to get a non-Gaussian and scale it by sigma. So here is divided by sigma, here is scaled by sigma. Consequently, xt is non-Gaussian. So, however, this approach is only good if it's weakly non-Gaussian. This approximation considers that the difference between the correlation in the non-Gaussian space and its corresponding value in the Gaussian space are not significant. In other words, again, it's weakly non-Gaussian, then it's okay, the spectrum, whether it's Gaussian or non-Gaussian are similar, correlation is similar. As simple as that. There are some algorithms developed by others, excellent researchers, trying to deal with non-Gaussian process. And one of the things that need to be done is to find something called underlying Gaussian power spectral density function or correlation, autocorrelation coefficient. There are some details that you need to shuffle and you need to readjust the probability level and so on and so forth. This makes it cumbersome. And there's another algorithm as well which will overcome the issue that associated with the Master and Gary's approach. The algorithm that I have in mind is developed by Shriver and Schmitz. Essentially, it says as follows: you give a signal to me, I can calculate the power spectral density. As we said, once you have power spectral density, what you can do is you can sort all the samples, and then the next step of IAAFT algorithm are as follows. You sample a sequence of Gaussian white noise. In other words, you're trying to disrupt the original signal or randomly shuffle it. Using a white noise of the same length, you calculate the phase. Once you have the new phase, you using the amplitude, power spectral density, you using the phase which is getting from white noise, then you calculate a new signal. This signal is different than your original signal, and you rank each value of these and represent the rank as Rj, and then you say, okay, this does not satisfy the power spectral density completely or the signal, then you reorder it according to the rank in here, and then you calculate the phase of according to reordering the sample, and you repeat the process. Then you get generating another perhaps non-stationary Gaussian process, whether Gaussian or non-Gaussian, it's okay, the same. But you say, why they are doing that? Those are physicists. What they wanted to do is test the hypothesis whether the process is stationary or not. In graphic form, basically you say, okay, originally I have the seed records. I want to generate a surrogate. What I do? I get the white noise, okay? From white noise, I get the phase. You have the amplitude, I get the, this signal, I get its amplitude. With the amplitude and the phase, I generate a new signal. However, this signal is not ordered according to what I had before, so I reorder it according to the probability distribution, like from the original record. And essentially, this is according to rank-based shuffling the signal. Once you have done this, every samples of this obtained signal is replaced by the samples from this distribution, and this is what you have. And you go to next cycle, you iterate until you sample match the power spectral density and also match the distribution type. So you think about that, you replace this distribution by an assigned non-Gaussian distribution. You can use it to simulate a signal, okay? Of course, the power spectrum, in other words, the amplitude, in this case, is obtained from Fourier transform. We said Fourier transform is good for stationary process. Consequently, this may not be good for non-stationary process. So what is non-stationary process? It's kind of very interesting that we are going to talk about. First, I will just simply mention the process that we saw. We extend IAAFT simply by generating the samples based on given marginal probability density function of the signal you wanted to generate, and repeat the process. And that is how you obtain at the end the generated signal you want. You say, what is a signal? A ground motion, a seismic ground motion is a signal. You go through these steps, and what you have is a generated signal. The signal generated must provide you the same power spectral density function that you assigned originally. You also need to satisfy the target probability distribution function. Okay, now we move on to non-stationary process. One of excellent work that was provided was by Bradley in 1965, and he defined a non-stationary process like that: xt equal to a ft ei 2 pi ft dzf. Remember, that was used to define stationary process Kramer's representation. Now, what he has done is add a modulation function. Modulation function depends on f, frequency, and also depends on time. So AFT is a slowly varying amplitude and modulation function. This part represents stationary process. So suggest to evaluate evolutionary power spectral density function by applying a short time Fourier transform. In other words, windowed Fourier transform. However, the forward Fourier, short time Fourier transform and the definition of evolutionary process do not form a transformation pair. In other words, there is no corresponding transform satisfy this definition. There's some kind of difficulty in using it. And when you use a short time Fourier transform to calculate the power spectral density, actually is an approximation. No unique inverse exists to compute the evolutionary power spectral density function suggested by Bradley from the correlation function of non-stationary, non-Gaussian process. This is elaborated by Shields and Dept in 2013. The estimation of evolutionary power spectral density functions through the use of continuous wavelet transform was suggested by Spanos and Faella in their estimation, two approximations also involved, similar to the short-time Fourier transform. Okay, so what I wanted to emphasize is, based on this definition, you can suggest the approximate way to calculate the evolutionary power spectral density function, but there is no inverse between in these two, or in other words, in time domain, or in the evolutionary process domain, let's say. Okay, so essentially, if you use a short-time Fourier transform, depends the window width you use. You can have a narrow window, okay? You have good time localization. If you use a very wide window like this, you have very good representation of frequency, but not time localization. You apply this short-time Fourier transform, what you have is this signal is represented by amplitude like that and the phase. In summary, short-time Fourier transform pair is a redundant, redundant transform. Short-time Fourier signal, if you apply inverse and the transform coefficient, you get the original signal. However, if I assign values in here, same value, and the different phase, I can apply inverse transform to get signal. But when I get the signal come back, they will not be equal to the coefficient. In other words, you assign a power spectral density, you go back to the time domain, you think you get a signal that has the prescribed power spectral density of, let's say, ground motion. Actually, you don't, because once you get him back, this does not hold. So this is not unlike the Fourier transform pair, which is a non-redundant transform. So again, this is redundant transform. There is a trouble in that. So what is really what is redundant transform? You think about, you have x equal to 10, you say the forward transform is split the value, 5, 5. You apply back transform, you get 10. So sum these two, you get 10. Now, if I give you y1, y2 equal to 7 and 3, you apply backward transform is 3 plus 7, you get 10. Then you apply forward transform, you split the 5, 5. This is not equal to 7 and 3. So one way it's okay, another way is not good. So there is an implication. Assign an amplitude or short-time Fourier transform that match the target amplitude, and the random process can obtain a signal by applying inverse short-time Fourier transform. But the obtained signal does not necessarily match the target amplitude. So bad luck. If you give a evolutionary power spectral density, when you generate it just like this way, the signal may not give you the desired power spectral density. So this is true in general for a redundant transform unless other conditions are imposed. Now, before I'm going to describe the IPAC algorithm that we developed, I'm going to just trying to think about how this works. Because sometimes this is difficult to understand why they get this representation to simulate evolutionary stochastic process. You can, as an engineer, you can easily look at this definition saying, I'm going to discretize this integral representation. Instead of dz, I'm going to represent the delta z. And because of that, I have this representation to simulate non-stationary process, evolutionary process. It's simple as that. No other theories. Intuitively, it's kind of nice. We like intuition. Okay? You look at the definition, you can directly convert to the spectral representation method, and this is your representation. If you like more about the mathematics behind it, you can look at these references about the step-by-step proof that is correct. Okay? Power spectral, the evolutionary power spectral density in this case is amplitude modulation function squared times the stationary process power spectral density. The phase is independent, identically distributed between 0 and 2 pi. So this is 0, 2 pi. So simple. You have non-stationary process, you just using in here, you using this formula, what you get is the signal. What is the problem? Again, the problem is that what you simulate in here is Gaussian non-stationary process or non-stationary Gaussian process. Okay, what happened if you want a non-Gaussian process? If you want a non-Gaussian process, there are algorithms. What you need to do involves iterative procedure, find something called the underlying Gaussian power spectral density function. So you want to know what's happening in the Gaussian space and find the corresponding power spectral density function. Once you do that, you simulate the signal. Then it's okay. But this takes some time, computing time, and the concept is not easy to swallow. Also, if it is evolutionary power spectral density function, coherence between two evolutionary processes is always time independent. You can extend that, talk about the sigma oscillatory process, Gonde and Penn and others. Okay, the idea of shield and deltatis is show some kind of iterative loop in here, and I'm not going to elaborate more about their process, but the idea, again, is you need to find the underlying Gaussian power spectral density function or autocorrelation function, so you can simulate in Gaussian space the signal, then convert it back to non-Gaussian, roughly that. So, coherence function between two evolutionary processes is always time independent. This restriction can be overcome, of course. Alternatively, one can use non-stationary complex or orthogonal basis function. Remember, sine and cosine are orthogonal basis functions. You can use any other basis function to generate in non-stationary process instead of stationary. For example, you can use something called a discrete orthogonal S transform or discrete harmonic wavelets to generate. Now, the real myths that what I want to talk about is as follows: the iterative power and amplitude correction algorithm, IPAC algorithm. To describe this algorithm, there are a few things I want to talk about. A few transform pair, S transform pair, and the continuous wavelet transform pair. I mentioned two. One is Morse, generalized Morse wavelet, another one is Morlet wavelet. The IPAC algorithm for non-stationary, non-Gaussian or Gaussian cases we can do is for single process and sample process for given target time frequency dependent power spectral density and the marginal power probability distribution function. We can generate in surrogates as well. We can generate in using the same algorithm with some modification. We can generate in random field. We can generate in vector of processes. So what all this is about, for example, you have a building. If you wanted to generate in ground motion at one point, it's a single process. If you want a field, let's say underneath of a dam, you want the whole interface, how the ground motion is moved, you generate in the field. For vectors, you can think about the bridges have a few supports. For each of the supports, the excitation are somehow partially coherent, so you needed to generate a vector process. Additionally, the other application that you can think of is as follows. In a bridge, a long span bridge and with few supports, you only have a record at a particular support. You do not have support at the other sides, and what you need to do is sample the ground motions, conditional you observe the signal, and to simulate the excitation at all other supports. Okay, so these are the usefulness of the IPAC algorithm. And I'm going to explain first what is S-transform. S-transform was developed by Stockwell, okay, and others. And actually, he did his PhD in the University of Western Ontario. Those are physicists or geophysicists. The transform is very similar to short-time Fourier transform, except that the window, you see now, depends on frequency and the time. It's kind of strange. Originally, short-time Fourier transform only depends on the width of the window. Now, you depend on a Gaussian function that is also function of f. So mass is like that. S transform pair is a redundant transform. So all the bad stuff associated with a short-time Fourier transform or non-redundancy, redundant transform applies in this case as well. However, it has good frequency resolution at a low frequency and the time localization. So we know at a particular time for a ground motion what is the energy distribution in frequency. So you apply short S transform to a signal, you apply inverse signal, you getting back the original signal. You apply assigned transformation coefficient, you get a signal, but then you reapply the transform, you get the transform coefficient that are not necessarily equal to the originally assigned value. So same as short-time Fourier transform. Okay, we needed to define the power spectral density based on S transform, and what we can define is using this formula. It can be shown that if you using this, is energy preserving. You have forward transform discretized form, you have backward transform discretized form. Therefore, if you have theta PQ independent uniform distributed, you can get a signal for sure. But how good is this signal to match given power spectral density and the marginal probability density function of a signal? We do not know yet. So again, could be considered to be sample error record, but this may not satisfy satisfactorily because of properties of non-preserving the amplitude. In other words, the energy is not the same you assigned. Deviation from marginal probability density function. So you don't know what is the marginal distribution of sampled signal. So those are the two bad things. Now, let's think about the continuous wavelet. That's kind of similar idea, but here, of course, is a mother wavelet. Okay, you have energy preserving definition of time scale as well, based on this. For example, you can find in very well-known textbook by Dow Beaches, and you need those constants to get the inverse and so on and so forth. In this case, given a signal, what you get is scaleogram or scalograms, not the periodograms, because S is scale, tau is the time localization. So for example, you have wavelets like that in time domain, and here is in frequency domain for most wavelets. You have molet wavelets, looks like this long equation in here. Okay, you write a forward transform in discrete form, you write a backward transform in discrete form, and again, you can assign the phase. Given the amplitude, you can get a signal. Has the same problem, non-preserving the amplitude, deviation from marginal probability density function sampled at xt from the target power spectrum, probability density function. So to illustrate how it looks like, you have this signal, this is Fourier transform, this is short-time Fourier transform, this ST transform, S transform. So this is continuous wavelet transform, discretized form, molet wavelets. So this is scale, this is frequency, okay, this is frequency, and so on and so forth. All here are the frequencies. Some of them are time and frequency dependent or time scale dependent. Here is the power spectral density function in the transform domain defined. There is no go back to evolutionary power spectral density. Whatever you get from the transform, it is. So no approximation involved except perhaps the use of single signal to estimate the power spectral density function of the process may associate with bias or variabilities or, variabilities. So This is amplitude, this is power spectral density in the transfer domain. The IPAC algorithm that we propose overcome some of the issues. So what we do? We says, you give me the probability distribution function of the signal, like a ground motion. So you have a distribution. Remember we talked about the marginal mixture distribution. So if you have a signal, ground motion signal have 3,000 data points, I put the 3,000 data points together, I have marginal mixture probability distribution function. You also give me the power distribution of transfer domain, no matter which distribution transform you give to me. The algorithm is simple, 1, 2, 3, 4 step. So first what I do, I sample the signal using the time domain, in the time domain using the marginal distribution. So we said, if you give me the marginal distribution, I can sample 3,000 numbers. That's no problem, right? Just sample it, okay? In whatever order, no particular order. We get a random phase to initialize the iteration. The random phase we can get from white noise. We sample the signal based on the target power distribution in the transform domain using inverse transform, including the initial random phase. Then once we get the signal as IAAFT, we find the rank of each value of the signal. Now we shuffle the value, what we get, according to its rank, put whatever place it is. If the signal that you obtain is 1, 3, 2, and the sampled signal, I find that the largest one, the rank 1, in the first place, find the third one, I only have 3, so third one in second, and the second one in third place. Now I'm done here. I then using the signal, going to find the phase from the step 3. Once that phase is obtained, I go back to 2 and 3. I repeat several times until convergence is achieved. Usually the convergence can be achieved about 10 iterations or 15 at most. Okay, so basically this is the diagram, how we do it. We iterate, sample white noise, find the phase, calculate the power corrected time series, so basically using assigned power spectral density, identify the rank of the sample, we calculate the amplitude corrected time series, we check the convergence, if not, go back, iterate until that. So there is no involvement of underlying Gaussian or non-Gaussian, whatever. Whatever distribution you assign, I just do this and went through this, then that's okay. For example, if I have this signal from Mexico, 1985 earthquake, I calculated its power spectral density, I get its distribution, I can resample a signal, and this is what I get, and this is power spectral density of this signal. As you can see, they are similar. So by using S-transform for a given record, I can use the same record, but now I using continuous wavelet, Morse wavelet, and I don't need to go back to frequency. Whatever scale it is, I operate the same way. I can generate in artificial surrogates for this signal, and the energy in time scale domain is similar or almost identical to the original signal. You say, so why bother if I have a signal, why you repeating to generating a signal? As we said, you can have two signals that looks completely different, yet they have same power spectral density. So surrogate acting like that. To see more application, we get in LSST, Taiwan's array of earthquake is located in very close about, for LSST, the distance between the records is about maximum 100 meters. So I can think all the records are come from same stochastic process. One of the signal at this point looks like this. I take 12 records, I take average of its power spectral density, use an S transform, it looks like that. I take it is continuous wavelet transform, average power, looks like this. Okay, I can use this or this as my target, power spectral density in the transfer domain. And I have a distribution because I can see the distribution is not Gaussian, the signal. So I have non-Gaussian signal. I simulate a signal. This is simulated signal. This is second simulated signal. If I simulate sufficient, like 1,000 of them, I calculate the spectra, looks like this. In S transform domain, in here is continuous wavelet domain. If you compare this one to previous one, they are very close. The spectrum of the simulated signal looks like this. Okay, this is each of them is a sample. This is the mean and the standard deviation. They are very close to the original signal that you have. You can also use a target power spectrum developed in the literature. We have one, but we did not use. We use one in the literature by Saavedra and Bocklisser. It's non-stationary evolutionary power spectral density. We assign the non-Gaussian characteristic. We have target, which represent this in the S transfer domain, and the Mollet wavelet domain looks different, of course. You simulate sufficient, you calculate the mean value looks like that. You calculate the standard deviation look like that. You calculate the difference between the target and mean looks like this. So it's relatively small. Of course, standard deviation is always exist because there is a record-to-record variability. In other words, you can do it, whether it's use an S transform or continuous wavelet transform, and this is a weakly non-Gaussian process. So it's very simple to use. We trying to play with the algorithm to see if it works for highly non-Gaussian process. This is hypothetical, looks like this, cumulative distribution, has nothing looks like Gaussian, and we carried out the analysis. As you can see, the difference if you amplify this, looks like this. If you use the S transform, looks like this. So this is very significant underestimation in here, but here is not. So different transform has different characteristics. Okay. I'm not going to discuss how to expand to random field, but essentially application is as follows. You have these two plates that move against each other. This is Tohoku earthquake. The plate, not Tohoku, Tohoku earthquake. And this is where the plate broke. If you use a Fourier transform as SRM to simulate, sometimes this thing moves places that shouldn't be. However, if you use the S transform, after a sequence, what you get is see the displacement of the two plates, how it moved for the Tohoku earthquake. You can use it to simulate the random field, the same algorithm using the same target power spectral density. I did not write the coherence in here. The coherence we used is from Lugo and Wang. We did not use on our own, so that we hopefully can convince people that it works. The kurtosis is 2.4 in this case. Remember, for Gaussian kurtosis is 3.0. And here is localization of X at different locations, how the signal looks like. We simulated the so to see whether the simulated field is good or not, we know the target power spectral density looks like that. Here is at 0, 50, 100 meters, and you calculate power spectral density, looks like this, which are similar to that. You calculate the average coherence, and the coherence matches the target coherence that was assigned. So simply says the algorithm works. Okay. So couple of observations before we extend it to vector of process. Because we want to maintain coherence, whenever you move the phase, you must synchronize the motion, the move of the phase. This has been discussed when using IAAFT by Schreiber and Schmitz for Fourier transform. And we extended, it says, if you use a time frequency type of transform, what you need to do is that synchronized phase motion move must be applied to both frequency and the time. So this is essentially the extension required. We have extended to the vector process. First, you need generating noise, white noise. You can use the so-called discrete orthogonal S transform or using SRM, since it's a white noise. Once you generate it, you get the phase as to initialize your process, okay? And the process is written in here. I expect it will take some time to explain it in details, but the essential idea is the same as IPAC for a single process. The only difference is that each time you move the phase for all the process must be synchronized. Okay, here is you can think about at 0, 100, 500, and 1,500 you have a support, for example, for a structure or infrastructure system. You want to model the excitation at these 4 points. You are given the power spectral density function here, and you can give them the power probability distribution function can be Gaussian and non-Gaussian, and you want, of course, you give the coherence. You want to simulate what is the ground motion at this point. The coherence is given, for example, in here. Instead of in mathematical form, you first simulate the white noise, as looks like that, and you iterate. What you get is these signals. This is power spectral density at each of the side. This is the coherence, time and frequency dependent coherence that you calculate from simulated record. Now, what happens is that single sample cannot tell us anything because it's a stochastic process. So we generated many of them, and you can look about what the mean looks like, standard deviation looks like for the power spectral density, for the coherence, and so on and so forth. And you can see there is a standard deviation of power spectral density as expected, because each record have its own variability. This is the last part. If the previous part are relatively simple, say for us to understand, then the last step to simulate a conditional simulation, if you wish, is also simple, because essentially you say the step 1, I'm going to sample a lot of unconditional, non-stationary, non-Gaussian process. Once I simulate it, I map the simulation to Gaussian process. That mapping is static. Do not need to consider what is the power spectral density or any other things. You can also mapping the conditions to non-Gaussian to Gaussian space. Once you map in the Gaussian space, we all know the generation of the conditional samples in Gaussian space is easy. Okay? So again, the essential idea is you simulate the non-stationary, non-Gaussian in originally unconditional. You map it to Gaussian space, including the condition. In Gaussian space, you carry out the simulation. Once you have it, you map it back to the Gaussian space. In here, the condition is involved. And what happens is you already generated your signal. Okay, so again, we consider the LSST or smart array. Looks like this. You have a bunch of records. And we say, okay, you want the simulating records conditioned to one of the points. You have the acceleration looks like that in 101, 106 in here, and you want to simulate C01. You do not know the signal, how it looks like. You are given these, and these you want to simulate this signal. You can see the signal is not Gaussian, and based on the process we carry out, you need to assign the coherence. And what happens is you can simulate the conditional simulation of two signals that match those conditions and give you signal at C01, conditional of observed ground motion at 101 and 106. To check whether the simulated signal match what is a given condition, first we check the power spectral density, then we check the coherence, and as you can see, the average match kind well to the target. So in conclusion, I can say three things. We review the definition of stationary process and the evolutionary process, and illustrate how intuitive the SRM is linked with a Fourier transform, and we emphasize that there is no consistent or exact transform pair relating the evolutionary process in the original domain and the time frequency domain. So evolutionary process is very pretty and beautiful, was developed by Bradley and has been extensively used by engineers for earthquake engineering and wind engineering. However, when you go in one way, you cannot come back, and vice versa. So in other words, you can define it as a spectral representation method, but you do not know which transform is exactly corresponding to estimate its power spectral density. Perhaps this is the criticism for a beautiful theory and worked very well, especially if we are interested in non-stationary Gaussian process. We highlight the important features of iterative amplitude adjusted Fourier transform, which was developed by Schreiber and Schmitz. We indicate the algorithm with minimal modification, as we have done, can be used to sample stationary non-Gaussian process for given target power spectral density function and the marginal probability distribution function. Remember, the marginal here we are talking about is a marginal mixture, so mix everything. You can talk about the marginal probability distribution with some kind of normalization. We propose an iterative power and amplitude spectral correction algorithm. We showed that the algorithm can be used in dealing with non-stationary, non-Gaussian or Gaussian process using transform pairs and providing time frequency or time scale decomposition. For example, you can use in short time Fourier transform, S transform, continue wavelet transform. So it is a very, very powerful tool to dealing with signals in seismic ground motions. Okay, the proposed IPAC algorithm is versatile, as we said. We generalized the IPAC algorithm so for multidimensional non-stationary non-Gaussian field. We extend the IPAC for vector process, as the IPAC algorithm can be used to sample non-stationary non-Gaussian field without first finding the corresponding underlying Gaussian characteristics. We propose a conditional simulation framework for the non-stationary, non-homogeneous, non-Gaussian or Gaussian field and the multivariate process. We showed the value or by numeric example. I did not do all these, and I have collaborated this with former and current students and colleagues, which I'm grateful for their contribution, for the information I have presented here. I also would like to acknowledge the financial support received from National Science and Engineering Research Council of Canada. And again, I would like to thank you very much for your attention and attending this talk. Thanks. No sé.
Muy bien. Pues después de esta plática matemáticamente intensa, pero muy interesante, me gustaría preguntar si hay alguna duda o pregunta aquí por parte de los compañeros. De los compañeros del auditorio. Entonces, tenemos tiempo para algunas preguntas. Sí, doctor López Batis.
Oscar López Bates, muchas gracias, buenas tardes. Hanping, te entendí como la 10ª parte de lo que dijiste. Ahora tengo una pregunta, si regresamos en las diapositivas, una pregunta muy... Sí, por favor. A donde estaba el ejemplo de que tenías unos puntos en círculo, ahí ya te pasaste. Los puntos en círculo es... Ahí, todo el procedimiento que estás marcando te permite, a partir de la información que tienes en 101 y en 106, estimar el C. Ahora, eso, estás asumiendo que el material en donde están, me imagino que es una superficie de terreno, pudiera yo pensar algo así. Esos puntos 101, 106 y C01, quisiera pensar que es una superficie de terreno.
Sí.
Y entonces, estaríamos partiendo del hecho de que la estructura del terreno es la misma en 101, 106. Y si no es así...
No sé cómo hacerlo. O sea, si el terreno es diferente, tiene como amplificación aquí. Amplificación.
Variación, pues, digamos.
Pero entonces no sabemos. Pienso que el suelo que está condicionado de la distancia de 0 a 400 metros es muy corto. A lo mejor propiedad de suelo no cambia tanto. Pero estoy completamente de acuerdo que si el suelo de este punto y este punto es diferente, entonces metodología se aplica, pero hay que considerar la amplificación en estos 3 puntos a diferentes.
Tanto en la estructura del suelo como la geometría en profundidad, todo eso.
Perfecto, sí.
Gracias.
Gracias a ti.
Si hay otra pregunta de algunos estudiantes que vinieron con nosotros, o no sé si en internet.
Bueno, sí. Le manda saludos el doctor Sánchez Esma.
Gracias.
También Juan de Dios le manda saludos. Y el doctor Sesma pregunta, me interesa mucho saber la experiencia del doctor Hong para aprovechar la localización en espacio y tiempo de la transformada S.
S es la transformada S. Pienso que la transformada S es mejor que short time Fourier transform, porque la ventana de la transformada S es frecuencia dependiente. Entonces, como la frecuencia disminuye, la ventana en el tiempo se amplía. A ver si puedo llegar a la transformada S. aquí. Como ves, si ese es muy pequeño, o sea, low frequency, entonces esta ventana es muy ancho. Si la frecuencia es alta, la ventana efectiva de este Gaussian window es muy corto, entonces por eso tiene buena good frequency resolution at low frequency and the time localization at high frequency. So I believe at least the S transform is better than short time Fourier transform. Also, there are studies indicating that the Morlet wavelet is very similar to S transform, or other way around. S transform is provide results very similar to Morlet wavelet. So that's our experience. Thank you. Gracias, Dr. Sánchez.
Bueno, la pregunta sería quizás una cuestión relacionada también con la ingeniería estructural, porque se menciona que cuando se hace análisis no lineal de estructuras es más conveniente utilizar registros reales comparados con registros sintéticos o simulados. No sé si hay algún comentario al respecto.
Cuando hacemos análisis no lineales sujeta a grandes temblores, sí preocupamos que signos artificiales no representa la energía distribuida en tiempo y la frecuencia. Si la distribución de energía en tiempo y la frecuencia está como temblores reales, uno no debería preocuparse tanto. Estoy de acuerdo, si esas dos condiciones son diferentes, entonces sí hay problema. Gracias.
No sé si hay más comentarios, preguntas. Si no, voy a de manera espontánea. Sacamos aquí un reconocimiento. Voy a leerlo. Vamos a entregar un reconocimiento y un presente para que se pague sobre equipaje, yo creo, porque está muy pesado esto. Entonces dice, el Instituto de Ingeniería de la Universidad Nacional Autónoma de México otorga el presente reconocimiento al profesor Hanping por impartir pues, la conferencia realizada el lunes 14 de noviembre de 2022 en el auditorio José Luis Sánchez Vibriesca de la Torre de Ingeniería de la UNAM, y lo firma la directora Rosa María Ramírez Zamora. Entonces hago entrega de
Muchísimas gracias.
Sí, el reconocimiento y también un presente que se llama El arte en la ciencia, patrimonio desconocido del UNAM, para que quizás en el avión o en el transporte pues se pueda ir leyendo.
Gracias, doctor. Gracias.
Y pues le damos un aplauso. Pues muchas gracias a los asistentes presenciales y también a los virtuales. Muchas gracias.
Gracias a ustedes por compartir el tiempo conmigo. Gracias.